After studying this module, you shall be able to study Freundlich adsorption isotherm, know the limitations of Freundlich adsorption isotherm, know the postulates and derivation of Langmuir adsorption isotherm, learn how Langmuir adsorption explains type 1 adsorption isotherm, and know about the alternate form of Langmuir adsorption isotherm. First, let us talk about the Freundlich adsorption isotherm. Out of the 5 different categories of adsorption isotherms discussed above, type 1 isotherm is the easiest to explain. One of the first attempts to explain type 1 adsorption isotherm was made by Freundlich in 1909. He gave an empirical relation between the extent of adsorption with pressure at a constant temperature, that is x by m equals to Kp raised to power 1 by n, where x is the mass of the gas adsorbed on mass m of the solid adsorbent at pressure P. K and n are constants for a given adsorbate-adsorbent pair at a particular temperature. Taking logarithm of equation 1, we get log x by m equals to log k plus 1 by n log p by p naught. This is our equation 2. Here P naught is the unit pressure. The validity of Freundlich isotherm can be verified by plotting a graph between log x by m and log p by p naught. A straight line with a slope equals to 1 by n and intercept equals to log k validates Freundlich adsorption isotherm. The two constants can be evaluated from these values. Figure shows the Freundlich adsorption isotherm. The value of n generally is greater than 1 and thus the reciprocal 1 by n can have values between 0 to 1. Based on this, Freundlich isotherm is able to explain the type 1 adsorption isotherm as follows. When 1 by n is equals to 0, x by m is constant. This means that extent of adsorption is independent of pressure. When 1 by n is equals to 1, x by m equals to Kp. This means that the extent of adsorption varies linearly with pressure. In the intermediate range, 1 by n varies between 0 to 1. This accounts for the fact that the increase in adsorption is not as fast as the increase in pressure. Although Freundlich isotherm gave satisfactory results, it was associated with certain limitations as follows. It was an empirical relation, that means there was no theoretical foundation. It could explain only type 1 adsorption isotherm. It failed at high pressures as the experimental isotherm approached saturation at high pressures, which Freundlich adsorption isotherm could not explain. K and n are not true constants for a particular adsorbate-adsorbent system. They showed temperature dependence. Next, we shall see the Langmuir adsorption isotherm. First, we shall talk about the postulates of Langmuir adsorption isotherm. On the basis of certain theoretical postulates, Langmuir proposed an equation showing the variation in the extent of adsorption with pressure. He successfully explained type 1 adsorption isotherm, in which at low pressure the extent of adsorption increased linearly with pressure and thereafter became saturated at high pressures. The various assumptions of Langmuir adsorption isotherm are as adsorption of adsorbate molecules takes place only on fixed number of adsorption sites that are available on the surface of solid adsorbent. Number 2, adsorption is a process of sticky collision. This means that when a gas molecule hits a vacant site on the adsorbent surface, it will get adsorbed. However, if it hits an occupied site, there occurs an elastic collision and the gas molecule gets rebound. This implies that the adsorption takes place only on a vacant site where each site can hold only one gas molecule. Number 3, all the active sites on the adsorbent surface are energetically equivalent. That is, they involve constant heat of adsorption. Number 4. The surface of solid adsorbent is assumed to be completely flat and uniform on microscopic dimensions. Number 5. Under the conditions of low pressure and moderately high temperature, a monomolecular layer of adsorbent molecules is formed on the adsorbent surface. This is particularly true as the influence of active site on the adsorbent surface usually extends up to 1.5 to 2 angstroms. Number 6. There are no interactions between the gas molecules that are getting adsorbed onto the adsorbent surface. That is, adsorption of gas molecules takes place independent of the occupation of the neighboring sites. These gaseous molecules are thus assumed to behave ideally. Number 7. A state of dynamic equilibrium exists as follows. M plus S gives Ms, where M is the free gas molecule, S is the active site on solid adsorbent, and Ms is the adsorbed gas molecule on the solid surface. This means that adsorption takes place on vacant sites and desorption takes place from the occupied sites till a state of equilibrium is attained. As per the law of mass action, rate of forward reaction, that is adsorption, is equals to Kf m into S, and the rate of backward reaction, that is the desorption, is equals to Kb into Ms. At equilibrium, rate of adsorption is equals to rate of desorption, which implies that Kf into m into S is equals to Kb into Ms. This is our equation 3. Or we can write K1 equals to Kf by Kb equals to Ms upon m into S as our equation 4, where K1 is the equilibrium constant for distribution of adsorbate molecules between the adsorbent surface and the gas phase. Now we shall see the derivation of Langmuir adsorption isotherm. On the basis of above postulates, Langmuir derived the equation as follows. Under conditions of constant temperature and pressure, let the number of adsorbate molecules hitting unit area of adsorbent in unit time t be equal to n. Let the fraction of surface area of adsorbent that is covered be equals to theta. Therefore, the uncovered surface area of the adsorbent is equals to 1 minus theta. Now, rate of desorption is proportional to theta, or we can say that the rate of desorption is equals to Kd theta, where Kd is the constant for desorption. The rate of adsorption will be proportional to the uncovered surface area of the adsorbent and the number of adsorbate molecules hitting unit area of adsorbent in unit time. The latter in turn will be proportional to the pressure of the gas. Thus, we have rate of adsorption is proportional to P into 1 minus theta, or we can say that rate of adsorption is equals to Ka into P into 1 minus theta, where Ka is the constant for adsorption. At equilibrium, we have rate of adsorption equals to rate of desorption. Therefore, we have our equation 5 as Ka into P into 1 minus theta is equals to Kd into theta. Solving for theta, we get theta equals to Kap in divided by Kd plus Kap as our equation 6. Or we can write theta equals to Ka by Kd upon 1 plus Ka by Kd into P as our equation 7. Or we can give theta equals to K1P divided by 1 plus K1P as an equation 8, where K1 is equals to Ka by Kd. This is known as the Langmuir adsorption equation. In deriving this equation, we have assumed that only gas is chemisorbed without dissociation on the adsorbent. If two gases A and B undergo non-dissociative mechanism on the same adsorbent surface, then the Langmuir assumptions give theta equals to Ka Pa divided by 1 plus Ka Pa plus Kb Pb as our equation 9. Now we shall see what is the physical significance of the constant K1. The constant K1 equals to Ka by Kd in the equation is called as the distribution constant or equilibrium constant for distribution of adsorbate molecules between the adsorbent surface and the gas phase as discussed above. From equation we get K1 equals to theta upon 1 minus theta into 1 by P as our equation 10. This constant K, being an equilibrium constant, is a function of temperature only. Thus, at constant pressure and varying temperatures, different curves having different values of K1 are obtained. Since the fractional coverage increases with the decrease in temperature, the constant K1 follows an inverse relation with the temperature. If we plot a graph between the fractional coverage theta and pressure P, it is observed that the former increases with the increase in pressure and approaches unity at high pressures only when the adsorbate molecules are forced to occupy every available site on the adsorbent surface. Figure shows the Langmuir adsorption isotherms for non-dissociative mechanism with different values of K1. The equilibrium constant K1 can be further used to evaluate the standard free energy of adsorption delta G naught and the isoteric standard enthalpy of adsorption delta H naught at a fixed coverage using the relations. Delta G naught equals to minus RT ln K1 as our equation 11 and d by dt of ln K1 equals to delta H naught by RT as our equation 12. In case the adsorption is accompanied by dissociation as depicted by the equations, that is M2 gas gives 2M on the adsorbent surface and 2M plus 2S gives 2MS, where the terms have their usual meanings as discussed. The rate of adsorption will be directly proportional to the pressure and to the probability that both the dissociated atoms occupy vacant sites on the adsorbent surface. The latter will be therefore proportional to the square of the number of such vacant sites present on the adsorbent surface. Therefore, the rate of adsorption becomes equals to Ka into P into 1 minus theta whole square as our equation 13. Similarly, the rate of desorption will follow the second order kinetics, giving rate of desorption equals to Kd into theta square as equation 14. At equilibrium, the rate of adsorption equals to the rate of desorption, that is Ka P into 1 minus theta square equals to Kd theta square as equation 15. Solving for theta, we have theta upon 1 minus theta equals to Ka by Kd into P, or theta upon 1 minus theta whole square equals to K1P, where K1 equals to Ka by Kd, or theta upon 1 minus theta equals to under root K1P, or theta equals to under root K1P divided by 1 plus under root K1P as our equation 16. This shows that the fractional coverage of the adsorbent surface weakly depends on pressure as compared for the non-dissociative mechanism. This is depicted in figure which shows the Langmuir adsorption isotherms for dissociative mechanisms with different values of K1. Now we shall see the explanation of type 1 adsorption isotherm. One of the main approximations for Langmuir adsorption isotherm is the formation of monolayer of adsorbate molecules on the surface of adsorbent. Therefore, mass of gas molecules X adsorbed on a unit mass m of the adsorbent will be directly proportional to the fractional coverage theta. That is, X by m is proportional to theta, or X by m equals to K2 theta. Substituting the value of theta from above, we get X by m equals to K1 K2 into P divided by 1 plus K1P as our equation 18. Using this equation, type 1 adsorption isotherm can be explained as follows. At low pressure, K1P is very much smaller than 1. Therefore, we have X by m is approximately equals to K1 K2P, or X by m is directly proportional to P. Thus, at low pressures, the extent of adsorption is directly proportional to the pressure of the gas. This explains the type 1 adsorption isotherm at low pressures. At high pressures, K1 is much greater than 1. Therefore, we have X by m is approximately equals to K2, or X by m is equals to K2. That means at high pressure, the extent of adsorption becomes independent of pressure of the gas. This explains the type 1 adsorption isotherm at high pressures. For intermediate values of pressure, the variation in the extent of adsorption is not proportional to the latter. This is because of the presence of a pressure-dependent term in the denominator of equation 2, because of which the denominator increases faster with pressure as compared to the numerator. Thus, x by m is proportional to p to the power n, where n varies from 0 to 1. Thus, under conditions of intermediate pressure, Langmuir adsorption can be reduced to Freundlich adsorption isotherm equation. Now we shall see the validity of Langmuir adsorption isotherm. The validity of Langmuir adsorption isotherm can be verified by the graphical method. Using equation 18, we have x by m equals to k1 k2p divided by 1 plus k1p, or 1 upon x by m plus 1 plus k1p divided by k1 k2. This is equals to 1 upon k1 k2p plus 1 by k2. Or we can write that p upon x by m equals to 1 upon k1 k2 plus p by k2 as our equation 19. A straight line plot between p upon x by m and p will validate the Langmuir adsorption isotherm. This will give slope as p by k2 and intercept as k1 into k2. From these values, the constants k1 and k2 can be evaluated. Figure shows the Langmuir adsorption isotherm. Sometimes deviations are observed from the linearity. This means that for a particular adsorbent system, plot between p upon x by m and p does not give a straight line. This may be due to the following reasons. Number 1 is that partial adsorption or multilayer formation of adsorbate molecules on the surface of the adsorbent occurs. The assumption of monolayer formation is applicable only under conditions of low gas pressure and high temperature. Any deviations from such conditions leads to deviations from linearity. Number 2, there occurs some chemical reaction between the adsorbate molecules and the adsorbent surface. Langmuir assumes that the gas molecules are ideal in nature and do not interact amongst themselves or with the adsorbent surface. Any interactions lead to deviations from the expected behavior. Number 3, the active sites on the surface of adsorbent are not energetically equivalent. Langmuir assumes that the surface of adsorbent is homogeneous and uniform, but in actual practice there occurs several crystalline imperfections and cracks on the adsorbent surface so that the affinity of each active site varies. Now we shall see an alternate form of Langmuir adsorption isotherm. Equation 1 can also be written in an alternative form that involves the volume of adsorbed gas. Since theta gives the fractional coverage of the surface area of adsorbent, it can be also written as theta equals to V upon V mono as equation 20, where V is the volume of the gas adsorbed under given conditions of temperature and pressure, and V mono is the volume of the gas adsorbed at sufficiently high pressure so as to form a monolayer on the adsorbent surface. Thus, we have theta equals to K1P upon 1 plus K1P equals to V by V mono as our equation 21, or V by V mono equals to 1 upon K1P plus 1 as equation 22, or P by V equals to 1 upon K1 V mono plus P by V mono as equation 23. This is the alternative form of Langmuir adsorption isotherm. A plot between P upon V and P gives a straight line with slope 1 upon V mono and intercept 1 upon K1 V mono as shown in figure. From these values, K1 and V mono can be evaluated. Figure shows the alternative form of Langmuir adsorption isotherm. Now, we shall see the advantages and disadvantages of Langmuir adsorption isotherm. Langmuir adsorption isotherm is associated with advantages. Number 1, it can explain type 1 adsorption isotherm. Number 2, adsorption of gases and solids can be explained over a wide range of pressure. Number 3, fractional coverage, that is the surface area of the adsorbent that is covered, can also be evaluated using Langmuir adsorption isotherm. Despite the above advantages, Langmuir adsorption isotherm has one major limitation of not being able to explain type 2, 3, 4 and 5 adsorption isotherms. Now we shall summarize what we have learned in this module. Freundlich gave an empirical relation between extent of adsorption and pressure at a constant temperature as x by m equals to Kp to the power 1 by n. It could explain only type 1 adsorption isotherm and was associated with certain limitations. Langmuir adsorption is based on certain theoretical postulates. The adsorption process is dynamic in nature. Langmuir assumes the formation of monolayer of adsorbate molecules on the surface of solid adsorbent. The gas molecules are also assumed to behave ideally. Fractional coverage is given by theta equals to K1p upon 1 plus K1p, where K1 equals to Ka by Kd as the equilibrium constant for distribution of adsorbate molecules between the adsorbent surface and gas phase. Langmuir adsorption equation can be written as P upon x by m equals to 1 upon K1 K2 plus P by K2. An alternative form of Langmuir adsorption equation is P by V equals to 1 upon K1 V mono plus P by V mono. Langmuir adsorption isotherm is valid over a wide range of pressure and successfully explains type 1 adsorption isotherm. However, it fails to explain type 2, 3, 4 and 5 adsorption isotherm.